Welcome all. Here we are going to discuss theorem 10.2 closed graph theorem. The statement is let x and y be Banach spaces and f from x to y be a closed linear map, then f is continuous. Okay, the map f from x to y is continuous. We will discuss the proof. Given x and y are Banach spaces and f from x to y is a closed linear map, let us define capital Vn to be the set of all x element of x such that norm of f of x is less than or equal to n for n equal to 1, 2, 3, etc. Now we need to show that some Vn contains a neighborhood of 0 in x. Now from the definition of Vn we can conclude that the union of Vn is equal to the full space capital X, and Vn is closed by the definition, and so Vn is equal to Vn closure. So that is equal to union Vn closure implies if we take the complement both sides, we will get intersection Vn closure complement is equal to empty, so that cannot be dense in capital X. Okay, then by Bayes theorem, since X is Banach, there should be at least one entry from this set such that that is not dense in capital X. Let it be VP closure complement. Okay, that is VP closure complement is not dense in X for some P by Bayes theorem. This means that there exists an element x0 in X and some delta greater than 0 such that the ball with center x0 and delta radius intersection with VP closure complement is equal to empty. Okay, that is from this we can deduct ux of x0 delta is a subset of VP closure since its intersection with VP closure complement is empty. So let it be equation number 1. Now we claim that the ball with center 0 and radius delta is a subset of V for P. Okay, for that choose x element of the ball with center 0 and radius delta. That means norm of x is less than delta by the definition. Then we can get norm of x plus x0 minus x0, that is equal to norm x, which is less than delta. This means that the element x plus x0 is an element of the ball with center x0 and radius delta, that is a subset of VP closure by equation number 1. Thus we have x plus x0 is an element of VP closure and x0 is also an element of VP closure. So we can say that there are X sequences Vn and Wn in VP such that the first sequence Vn converges to x plus x0 and the second sequence Wn converges to x0. So Vn minus Wn converges to x. But if we check norm of f of Vn minus Wn, we get that is less than or equal to 2p. That means Vn minus Wn is an element of V2p. That means Vn minus Wn converges to x, implies x is an element of V2p closure. Thus the ball with center 0 and radius delta is a subset of V2p closure since we have taken x from the ball and now we have showed that x is an element of V2p closure. This leads to equation number 2. Okay, now let x element of the ball with center 0 and radius delta implies x is an element of V2p closure by equation number 2. This means that every neighborhood of x contains elements of V2p. So we can choose x1 element of V2p such that the norm difference with the point x is less than delta by 2. Okay, from this we can deduce that 2x minus 21 is an element of the ball with center 0 and radius delta. That means x minus x1 is an element of half of the ball with center 0 and radius delta. That is x is an element of V2p plus half of ux of 0 delta. So x is an element of actually from the ball with center 0 and radius delta. So we have arrived at the center, the ball with center 0 and radius delta is a subset of V2p plus half of ux of 0 delta. Let it be equation number 3. Now we rename the ball with center 0 and radius delta equal to u and V2p equal to v and k equal to 1 by 2. Then we have from the equation 3 that U is a subset of V plus KU. Then we can use the lemma 10.1 that there exists a sequence Vn in V2P such that x minus V1 plus 1 by 2 V2 plus etc plus 1 by 2 raised to n minus 1 Vn is an element of 1 by 2 raised to n into U of 0 delta. That is x minus V1 plus V2 by 2 plus etc plus Vn by 2 raised to n minus 1 is an element of 1 by 2 raised to n U of 0 delta. Let it be equation number 4. We will define Wn for n equal to 1 to 3 etc is equal to the term which is in the brackets. That is V1 plus V2 by 2 plus etc plus Vn by 2 raised to n minus 1. Then from equation 4 we get x minus Wn is an element of 1 by 2 raised to n U of 0 delta. That is 2 raised to n into x minus Wn is an element of U of 0 delta for every n. So the norm of 2 raised to n into x minus Wn is less than delta by the definition of the ball. Implies norm of x minus Wn is less than delta by 2 raised to n for every n. This means that as n tends to infinity, norm of x minus Wn tends to 0. And this means that Wn, the sequence Wn converges to x as n tends to infinity in capital X. Let it be equation number 5. Also, for n greater than m, if we check norm of f of Wn minus f of Wm, we get that is equal to norm of capital F of summation j equal to m plus 1 to n Vj by 2 raised to j minus 1. That is less than or equal to summation of the summation j equal to m plus 1 to n norm of f of Vj divided by 2 raised to j minus 1. We know that Vj is a sequence, Vn is a sequence from V to P, and so norm of f of Vj is less than or equal to 2p, and from this we get less than or equal to this quantity is less than or equal to 2p into summation j equal to m plus 1 to n 1 by 2 raised to j. And the summation is a geometric series with first term is 1 by 2 raised to m and the common ratio is 1 by 2. So we are applying the formula for calculating the sum with modulus of r is less than 1. We know geometric series converges, and so we get the quantity is 1 by 2 raised to m into 1 minus 1 by 2 raised to n minus 1. So this is equal to 4p into 1 by 2 raised to m minus 1 by 2 raised to n, which is less than 4p into 1 by 2 raised to m, since the term 1 by 2 raised to n is clearly positive. So that is we get for n greater than m, norm of f of Wn minus f of Wm is less than 4p by 2 raised to m. Now we check when this quantity 4p by 2 raised to m is less than epsilon. We conclude that this happens only if m is greater than log 4p by epsilon to the base 2. So we conclude that norm of f of Wn minus f of Wm is less than epsilon for all n greater than m, which is greater than log 4p by epsilon to the base 2. This means that the sequence f of Wn is a Cauchy sequence in Y, and we have Y is a Banach space, and so this sequence converges in Y. Since f is closed, if the sequence converges in Y to a point small y, then we can write Y is equal to capital F of x by the closeness of capital F and by equation 5. So that is f of Wn converges to f of x in capital Y. Let it be equation number 7. Okay. Now in equation 6, if we let m equal to 0 and w naught equal to 0, we get norm of f of Wn minus f of w naught is less than or equal to 4p by 2 raised to 0. That is norm of f of Wn minus f of 0, that is when w naught equal to 0, is less than or equal to 4p. That is norm of f of Wn is less than or equal to 4p for every n element of n. Let it be equation number 8. Hence, if we let f of x, we have f of x is equal to the limit of f of Wn by equation number 7. That is f of x equal to limit n tends to infinity f of Wn. So this means that norm of f of x is less than or equal to 4p by equation number 8. Hence, we have concluded that if x element of the ball with center 0 and radius delta, norm of f of x is less than or equal to 4p, means x is an element of V4p. That is, the ball with center 0 and radius delta is a subset of V4p as we claimed. So by theorem 6.2, we can conclude that f is continuous. Since theorem 6.2 says that if the function f is bounded on some closure of some ball with center 0 and radius r, then we can clearly say that f is continuous. Since u of 0 delta is a subset of v 4p, and in v 4p we have norm of f of x is less than or equal to 4p, we can clearly conclude that f is bounded on this ball with center 0 and radius delta. So by 6.2 we have concluded that f is continuous. Thank you.